In March 1989, the Hydro-Québec power system collapsed in a matter of seconds. Transformers caught on fire, and millions suddenly lost electricity. The cause of the collapse originated 93 million miles away. A massive sunspot, 54 times the diameter of Earth, had erupted, sending a surge of magnetic energy directly toward our planet. We live deep inside the atmosphere of an active, highly volatile star, yet for most of human history, we have operated completely blind to its weather patterns. Back in 1859, during the most powerful solar storm ever recorded, our technology was largely immune. We relied on brass telegraph keys and paper tape to communicate over long distances. Since then, we have built a civilization that runs almost entirely on electromagnetism, turning our modern infrastructure into a giant antenna to capture solar weather. Today, our vulnerability extends far beyond the ground. We rely on a delicate web of satellites and GPS networks orbiting in exposed space. For astronauts living outside the protective bubble of Earth's magnetic field, the risk is intensely biological. To measure exactly what happens to a human body during a solar storm, NASA placed an artificial dummy named Fred aboard the space station, physically packing his synthetic organs with sensitive radiation detectors. The threat is amplified by what physicists call stealth CMEs. These are massive explosions of solar plasma that erupt without any obvious visual warning signs on the sun's surface, striking Earth entirely by surprise. We have constructed an intricate electronic society, but we are navigating the solar system without the meteorological tools needed to see these stealth cosmic threats coming. When a solar storm strikes, it usually arrives in 3 distinct waves. The first is a solar flare, an intense burst of light and X-ray energy that reaches Earth in just 8 minutes. This flash strips electrons from molecules in our upper atmosphere, instantly blacking out high-frequency radio and GPS signals. Then comes the second wave, a solar particle event, or SPE, driving high-energy protons toward our planet. These protons pierce through spacecraft shielding to trigger phantom computer commands. They also force commercial airlines flying near the poles to quickly reroute to avoid heavy radiation exposure. Finally, the third and slowest wave arrives days later. These are coronal mass ejections, billion-ton clouds of magnetized plasma. When a CME collides with Earth, it violently distorts our magnetic field. This forces rogue direct current straight into the alternating current systems of our high-voltage electrical transformers. Dissecting this 3-wave sequence is helpful, but reacting to an attack is not a defense. We need to know when the weapon is being loaded before it fires. To solve this, researchers recently fed 50 years of satellite X-ray data into machine learning algorithms, searching for hidden patterns in the sun's behavior. This animated diagram visualizes what they found: 2 distinct intersecting natural rhythms. One is a 1.7-year cycle, and the other a 7-year cycle of energy buildup. As we see here, when these specific cycles align and peak simultaneously, the risk of a catastrophic superflare skyrockets. By mapping these cycles, mathematical models can now pinpoint exactly which timeframes and which specific latitudes on the sun are most dangerous, up to a year in advance. We are no longer waiting to react to random acts of nature. We are calculating the long-term probabilities of our local star. But predictive math requires continuous physical observation. To make these models actionable, the European Space Agency is building the Vigil mission. Right now, our Earth-based satellites suffer from a severe geographic limitation. They can only look at the sun face-on. This schematic outlines a different approach. Vigil parks at Lagrange Point 5, trailing far behind Earth. From here, Vigil has a clear view of the sun's side, monitoring turbulent magnetic activity days before the sun's rotation brings it into our direct line of sight. By stepping off the direct Earth-Sun line, we gain a deep space high ground, effectively eliminating the threat of invisible stealth CMEs. When Vigil is operational, its side-angle data will merge with our Earth-facing sensors to generate a continuous 24/7 space weather forecast. A confirmed 4 to 5 day warning provides the exact lead time needed to safely reroute polar flights and command multi-million-dollar satellites to fold panels into safe mode. On the ground, power operators can use that time to reduce grid loads and physically disconnect vulnerable transformers, preventing rogue currents from sparking catastrophic fires. We cannot stop the sun from erupting, but through the application of precise space meteorology, we take an event that could crash a civilization and reduce it to a passing cosmic rainstorm.